Thank you so much for joining our webinar on four uncertainties for green hydrogen technologies. And this is, of course, a forced technology perspective, but we do have a broad industry interaction, so we believe it's quite representative of what's out there. Today will be four speakers, not only me. My name is Ditte Bangsgaard. We also have my colleagues Ida, Christian, and Rian. Ida, Christian, are based in our head office in Brøndby, whereas Rian is in Esbjerg. But as you can see on the map, we are represented all across Denmark, also Scandinavia. A few practicalities. Today, your mics will be muted and you're able to write questions in the Q&A, and we will get back to you after the webinar. Please write your name and email, and we'll follow up. And it could be questions to the content, also wishes for future webinar content, or any other comments. And after the webinar, you will receive the slides. If it has any interest, we also have a LinkedIn group, Hydrogen Handling. You can see it in the image. But if you don't know us at Force Technology, we are the largest research and technology organization in Denmark. We're independent, self-governing, non-profit. We have a strong Scandinavian base. Both Norway and Sweden, we are heavily represented, and we provide services to the international market. As for hydrogen, we have services within materials and welding, testing, fracture mechanics, both the testing part and the calculations. We work with flow metering, measurements and simulation. Metrology, we have a huge gas loop environment. Emission measurements, which is indeed a very important aspect of Power-to-X. We don't want the green hydrogen to escape. And of course, on-site inspection and our whole NDT area is quite large. And then I'll let Ida jump in from here.
Thank you, Ditte. Yes, hello everyone. My name is Ida. I would like to say that in the work towards adapting new solutions for green hydrogen to become a natural part of our daily lives, Force Technology has tried to meet the different uncertainties of what you meet on this journey by creating a mini guide where we have four important aspects on hydrogen infrastructure. These four different points are how you get an overview of all your potential risks along the way, the suitability of components and materials, and what does hydrogen readiness mean, as well as how you should and how much you should document on your way on this process. And I will just try to change the slide and try again. Yeah. So to begin, I would like to talk about the materials and the components for your screening process. For metals, we have a risk of hydrogen embrittlement. This is important because it appears without warning and cracks propagate fast. You can see here an example from a bolt where the crack initiation happens on the bottom surface. For hydrogen embrittlement to occur, we need 3 different factors. So it really comes down to having a susceptible microstructure, having applied stresses, and being in an environment with enough hydrogen. So you can have different stresses from operational and residual stresses, and several other Yeah, thanks. For the environmental part, Christian will go into a bit more detail for that with the impurities and temperature. And I will begin with the material susceptibility, where, for example, microstructure and hardness is fairly important. So hydrogen embrittlement is affecting the material by decreasing the ductility and the strength. Here you can see an example with a material in two different environments. And in the environment on the right, we have hydrogen, and the crack looks fairly different from the first one. Actually, the crack growth can accelerate up to 10 times faster than in other environments. And if that's not enough, the crack can propagate spontaneously, even after years of operation, without warning. Luckily, we do have places where we can get help to screen materials for hydrogen compatibility. One example is the ASME B3112 on metals. Often these are non-mandatory overviews and with fairly little details. So you should always consider your specific situation and consult an expert when in doubt. These things changes along the way. The last edition of this one had, for example, titanium and alloys as an acceptable hydrogen gas compatibility. And now there's data showing that it can create titanium hydride formation. So this has changed. Often these overviews are quite similar. A lot of them agree that, for example, cast iron is not suitable for hydrogen use. But again, you should be aware of the little details and consider your specific situation. For polymers, the risks are, for example, blistering and leaks. And they are typically evaluated by permeability, diffusivity, and solubility. And one example of where you can get an overview will be the Sandia report. And some things changes when you have the hydrogen environment. Here you can generally say that permeation and strength are two things that you should consider when working with the polymers. So for components, you should consider when reusing and designing these things as well. It's not always easy to make a direct switch for a new situation. And Rian will go into this figure later on as well. But I can say that one of the places where you can get help on screening components will be, for example, a publication from Marcogas, again with a very simplistic view on if it's directly applicable or you need more information. And one example is valves that is developed well for natural gas purposes, but we need more information for or modification for using it for 100% hydrogen. I can also mention that recently there has been published a project called Future Grid from the UK, stating that they could use infrastructure, existing infrastructure from natural gas industry for 100% hydrogen use. You should just be aware that this happen for their specific conditions, and again, always consider your own specific conditions and consult an expert when you're in doubt. And now Christian will take over.
Hello everyone, my name is Christian, and I'll be talking a bit about the uncertainties that arises from gas purity and its effect on what we call hydrogen readiness. So from a gas purity perspective, what would hydrogen readiness mean? In my opinion, it means that you should know what hydrogen quality you will need, and maybe even more importantly, you should know what hydrogen quality you will receive. Because you might expect to receive 100% pure hydrogen, but in all likelihood, you won't. This is largely due to the fact that impurities are introduced during all stages, from production to handling to storage, and even from the infrastructure itself. Of course, it can be expected that the initial purity you'll receive will be different from the purity you will receive when the technology has matured a bit more. A simple reason for this could be that dedicated infrastructure, as opposed to refurbished pipelines, could be used in the future. Additionally, you should also consider that the local infrastructure, the local handling, storage, and so forth, all contribute to introducing impurities. And that these impurities might vary from one location to another. You can't expect to see the same impurities in your hydrogen if you have a site located in Northern Europe and one in Southern Europe. You should expect there to be a difference between the quality of hydrogen you will receive. Now, looking at hydrogen as a source of heating, you might assume you wouldn't really need to concern yourself with impurities. The hydrogen is just for burning, basically. And you would probably want to accept some level of impurities, as this would keep the cost of the hydrogen gas lower. In contrast to other industries where you might need high quality hydrogen, the hydrogen will of course be a more expensive gas to procure. However, when you want to just use it for heating, you can accept more impurities, because what you're actually interested in is the sort of warp index, or you could call it the output of the combustion. So as long as the warp index falls within your sort of specified range or expected ranges, you can be quite satisfied with it. There's a small detail, however, which means that depending on what impurities hydrogen gas might contain, you could expect like sulfur, maybe a bit of ammonia in some cases. It could provide some long-term risks for your setup if you've designed your heating system to handle high purity hydrogen. Well, could it accommodate a bit of sulfur, maybe some sulfide compounds, maybe some ammonia compounds, or would those create sort of long-term risks? So even if you're just using the hydrogen for heating, maybe you could consider even sort of stepping up the purity a bit to maybe counteract the risks that in some impurities might impose on your system. Moving on to the impurities themselves, they're not just one big blob of impurities that have a given effect. The effect of each impurity is unique, and the magnitude of the effect is also different between impurities. Think of high purity hydrogen. If you have small quantities of, for instance, hydrogen sulfide, you might actually see quite a drastic reduction in your material's susceptibility to hydrogen embrittlement and fatigue crack growth. On the other hand, if you look at the oxygen or carbon monoxide, you might see a marked increase in your sort of protection against the same effects. Specifically with fatigue crack growth, we have quite a solid understanding that oxygen and carbon monoxide protects and inhibits the effect. We assume, based on research that we've seen, that it's due to the oxygen and carbon monoxide competing with sites on the material surface, which will prevent the hydrogen from disassociating and in turn from entering into your material. Some other known effects of impurities would, as I mentioned, hydrogen sulfide, or I think is methylphenol, where you see a marked increase in the susceptibility of your material. However, there is still quite a limited understanding of impurities' effects on your materials, especially if you begin to introduce the interplay between different impurities. As you can see on the figure, carbon monoxide doesn't seem to have a big impact. Water seems to have a slight impact. If you mix the two, you make carbonic acid. What's the impact then? And you can make similar sort of mixtures of all of these different impurities and consider, well, could this one be especially potent, either as a inhibiting effect or a more destructive effect instead? The picture only becomes more complex when the system-specific factors are taken into consideration, effects such as the pH, temperature, pressure, presence of, for example, chlorinated compounds, or even certain microbial effects. As an example of this, the figure on the right, you can see a rough evaluation of performance of nickel-containing alloys in a high temperature and highly alkaline environment under the presence of several bars of hydrogen pressure. In this case, nickel content increases corrosion resistance in the alkaline environment. However, as your nickel content increases, so does your susceptibility to hydrogen embrittlement. So further adding complexity to even this situation, what if you put strain on it? Does the system have some operational conditions? Do you have variations in pressure? Do you have variations in temperature? The rough evaluation you could make from these different aspects would be that you have a sort of Goldilocks zone in this example, where you have a better performing alloy, where you maximize your nickel content, but stop adding nickel before your alloy becomes susceptible to hydrogen embrittlement. So, as you can probably tell, it rapidly becomes quite complicated as you introduce further aspects for consideration. Ideally, you'd want to minimize as many uncertainties as possible, which, of course, due to the so far quite limited research on the subject, is easier said than done. However, it's not all doom and gloom. There is limited research on the topic of impurities effects, but we do have some data. As I mentioned earlier, carbon monoxide and oxygen both appear to be potent inhibitors of fatigue crack growth. And as can be seen on the figure on the right, if you add about 850 parts per million oxygen to your hydrogen, you can almost eliminate, but at least highly diminish the effects of hydrogen on fatigue crack growth rate in this specific system. But as you also tell, you don't need 850 to actually diminish the effect. You need like 100 ppm or 250 ppm even, and you already see quite a marked difference. So consider that maybe if your system can accommodate or could be designed to accommodate the presence of a bit of oxygen in low concentrations, of course, you might be able to reduce the effects of fatigue crack growth. Of course, you need to make sure that you don't end up with some explosive mixtures, because oxygen and hydrogen have sort of a reputation of being able to detonate. So if you can control that and you can accommodate it in your system, you can diminish the effects of fatigue crack growth. And then finally, we can also just mention that while it seems quite complicated and complex, we are hopeful and we look forward into the coming years, because we expect that there will be quite a few more studies on the effects of impurities and their sort of combined effects with hydrogen on materials. Because as the technology and the industry matures, so we'd also expect the knowledge base to grow and mature with it. And of course, we here at FORCE are also working on our own understanding, and later on, Dieter will also give a short overview over some of the testing capabilities we are working on here at our offices. So I will just end my part with sort of a reiteration of my first slide, because I hope you know, if you didn't already, and you understand why I emphasize that you should both know what hydrogen quality you will need, but also, as I said, more importantly, what you will receive. as even small variations in the quality of the hydrogen can have quite a significant impact on the effects on your system. And I will let Rian take it from here.
Thanks, Christian. Let me just share my screen here. Okay. Just a sanity check. Christian, can you see my screen? Hydrogen ready? Perfect.
Yes.
Okay. So we've heard the term hydrogen ready today, and I'm sure you've also heard it previously. You may even use it yourself. One of the uncertainties we have is, what do we mean by something being hydrogen ready? And are we looking at it from a legislative perspective, traceability, measurement, even a marketing? Is it something, a label that we need to put on there so we can sell it? So this is quite a big uncertainty, and it's the start. If we can define what sort of readiness it is we're looking for, then we can find a strategy to demonstrate that readiness. And to help us, we can look at it two ways. We can look at compatibility and suitability. Now, the hydrogen compatibility tells us about the general use, whereas the hydrogen suitability will tell us more specific use, and that will include the impurities that Christian has spoken about, the materials that Ida has spoken about, pressures and temperatures. So that's another important thing here is if we can differentiate between something being hydrogen compatible, which is a general use, and something which is suitable, which means it's been tested specifically for these conditions. And some of those conditions are here. Pressure cycling, temperature fluctuations, leakages, rapid decompression, ignition sources. This is just a short list. But if it is in your interest to define what you mean by hydrogen readiness, it's what is the uncertainty to overcome is, well, what are the conditions? What are those specific conditions? Then we also need to ensure that we have traceability to demonstrate. So we want to establish our own definition of hydrogen readiness, and then we need to demonstrate, well, this is my definition, and this is the things I've done. These are the tests and the evaluations I've done. This was my strategy to prove that it is hydrogen ready, or to demonstrate that it's hydrogen ready. And what we've seen in the past few years is that there's quite a bit of work that's been happening to try and figure out, what are the rules, what are the gaps, how do we get there? And here we can see some of the publications that in the last few years. But this is a field that will grow. And for me, a very important document was a study done by the European Clean Hydrogen Alliance. And they did a gap analysis. They built a roadmap for hydrogen standardization. And what they did is they looked at 400 topics in the hydrogen value chain. It looked at everything. It looked at technical things all the way through to politics. What is the invasion of Ukraine? How does that influence our own ability within Europe to be self-suppliant? So they looked at all of that, and they came out with some priorities. They also came out with a gap analysis to say, this is where we are in terms of the rules for hydrogen, that we need to demonstrate the hydrogen readiness of it. And just as an example, there are a lot more. This is just one snippet from the roadmap. Is we can see that for under development, if you look towards the middle there, we've got a space, 2023 to 2030. It's probably going to, some places will take longer, but there's going to be a gap where things need to be developed, then they need to be in place, and then they need to be in use. So the unfortunate thing, but it's also something that we realized, is that we don't have everything. We don't have all the rules. We don't have everything in place yet to demonstrate, according to old rules, the old way of doing things, that we can, that our product is, or our item is hydrogen ready. As an example, if we look at some technical specifications here, um, if you look at the boxes that have got a red outline, those give us the standards, and we can see, some of these standards have to be identified. Some of them are under revision, and some of them are in preparation. By the way, I forgot to say, this is a European perspective, so it doesn't, it looks at the state in Europe. So we need to identify things. Some of the ones that have been created, they need to be revised, and some are in preparation. And this is going to take several years, and we have a gap that we need to work on. So some of you may be familiar with this. It's just a simplified version, the CE mark. So the simplified version is that we look at the EU directives, or you look at your local requirements, your local regulations, whichever country you're in within the European Union. You then pick out the rules that, or the standards that they require you to use, and generally those are the harmonized standards. We then do our work, create the evidence, put it in a technical document package, do a conformity assessment, and that's it. We get the CE stamp. The thing is CE ready. But what we find now with hydrogen is that there's something new. We need a bit of a modification. And what are we seeing? It for now, there's a bigger risk. There's a bigger there's a bigger focus needed on risk assessments and risk management. So in addition to working to our harmonized standards, we now need to do a bigger job of the risk assessment, and put the evidence in place, and then present that to the permitting and authorizing authorities, and to the decision makers. So we're not going to have harmonized standards everywhere available. So we need to do this risk assessment and find out, okay, what are the big risks here, and then create some activities to cover those risks, to show, okay, this is how we're going to manage those risks. Then we do the evaluation. So first we identify the risk, then we need to evaluate how we manage that risk. We then get a set of data to say, okay, this is how we evaluated it. This easy example. We test the materials or the component with specific impurities. We then get the answer. We then evaluate whether that has shown that we are managing the risk. This is then put into the technical document package. So 80% is the same, 20% this addition is just a bigger risk assessment is needed. Then the other thing that we need to do is we'll need to monitor and report once it's in use. So where there was a gap, but we need to have something ready for industry, for the stakeholders, is we put it into operation, and then we'll also have to monitor it and report back to the stakeholders to say this is how it's happening. So that's what we are seeing. The general strategy is this inclusion of a bigger, greater focus on risk management, and also then to monitor and report on the findings. Now, most of the documents that you'll read, the latest documents, they're going to refer you to risk assessment. And they may refer you to a typical standard or a report or a document, or as we see here by the Institute of Gas Engineers and Managers, that they actually have a flow chart that we can follow. So the way we do it will depend on your situation, the specific risk assessment. There are a few ways to do it, but there is this guidance out there. And that is it from me for now. I would like to pass you over to Dita for the next part of the presentation.
Great. Thank you all. So now we presented a lot of uncertainties, and of course we need to build things. We need to evaluate if we can reuse or repurpose existing infrastructure and components. So how do we close some of these gaps? Well, I'll just see if I can move here. One way is standardization. We are converging to obtain some uniformity, but right now what is happening is a lot of standards are looking into, well, do we need a specific version to cover hydrogen? At Force Technology, we participate in the standardization processes on a national level, and we also participate in international working groups where we see a benefit also to be able to take home all the knowledge and spread within Danish industry and of course internationally. That covers ASME 3112, which is the most widely applied standard for hydrogen pipelines and piping, but also more widely applied at present because it is a standard covering something with hydrogen. Another important update to follow is the IGEM and the IGA, which are UK and European guidelines on hydrogen infrastructure. On components such as valves, we have the API 60, where we've also participated in the commentary on the new version, where there's an annex on how to evaluate valves for hydrogen service. And of course, as Rian mentioned, we have the European context, we have the American context, but at present it is mixed and applied across borders. Some of you may know the NACE MR 0175 or ISO 15156, which is for sour service oil and gas, where you have the presence of hydrogen sulfide, where you will get a lot more hydrogen into a material as compared to hydrogen gas. So some of these guidelines also refer to this, and it is being updated at present. So of course we will keep you posted if it becomes relevant in any situation. But it's definitely considered quite widely also for hydrogen gas purposes. DVGV, the German guidelines, are also published and applied quite widely in industry. So that's interesting to follow anyway. And we have, of course, because hydrogen is not new, it's just for the most part been confined in refineries, and now it's moving closer to the public, such as through refueling stations, and that's what the ISO 19880 covers. And publications and updates on that standard and the different subversions of it is also ongoing, and we're following that. Sandia in the US have done a lot of materials testing, and of course we also look at what's out there for materials test results. But what we also do is close the gaps with our own testing facilities, because a lot of academic work is being conducted, but how does that apply to real life purposes? Right now, we have no single harmonized way of testing for hydrogen compatibility and suitability. So we, with the knowledge of standards and materials, navigate and provide our best estimate of how do we do this in a safe way, but also not overdo it. As an example, well, just test methods and considerations of the most suitable test method and evaluation could be discussion on what is a short-term test, what is a long-term test. How do you get hydrogen into your material? A lot of the data that exists at present is done with electrochemical charging, which is not hydrogen gas, so you get typically more hydrogen into a material. That's being discussed if it can be applied or to standards. That's not the case at present, so we have to test with hydrogen gas. For the fracture mechanics, the test methods are being discussed, which is the most representative of your material, which is the most conservative. An example of that is two ASTM methods, 1681 versus 1820. And the whole aspect of acceptance criteria and the method of how do you evaluate your item or your material, your component post-testing, is also not standardized. So right now we're in a place where we need extensive testing to close the gap on some of the uncertainties, and we are participating in that. This is some of our new test facilities for hydrogen. We have a history of testing for oil and gas, offshore wind, but our current test facilities did not allow for hydrogen gas testing. It needs a lot more risk and safety considerations. So to the left, you can see our autoclave, which is a pressure chamber for hydrogen testing, which can be applied for fracture mechanics, also all sorts of other materials. We can load them. So you have, as Ida mentioned in the beginning, the hydrogen exposure, you have your material, and then you can apply different stress levels. So the three factors come into play. We can expose samples up to 500 bars hydrogen pressure and up to 200 degrees Celsius. But one thing is the materials. Then when you combine them in a component, then what happens? And that's what you see in the right image. We have a test rig for components such as valves, where we're able to cycle pressure, monitor fugitive emissions, leaks. Our experience with special testing tells us that typically it's not the metallic component being the weakest link. It is typically where you have gaskets, joints, other aspects to consider. And this is also possible to conduct tests with actual functionality testing of the moving parts. So that's something we look forward to present more results from. In general, we have been working with hydrogen testing over a lot of years. Another aspect such as hydrogen permeability, how much hydrogen actually goes into the sample. Does coatings have any barrier effects? What about sealing and gasket materials? These are also some of the things that we can test separately. The fracture mechanics, as I mentioned, and then large-scale component testing, where we build special test setups, is also something we can provide. So please reach out if you have any considerations, and we can see if we can provide any possibilities. Another way of closing the gaps at present is through research and development projects. And currently we have a wide range of projects ongoing on documentation demands, and testing for hydrogen compatibility as input for future standardization, because yes, we need the standards, but we also need the right evidence and knowledge into the standards, so we don't end up with standards that become an obstacle when we implement and accelerate the Power-to-X business. Technical requirements for Power-to-X facilities is another subject. Safe storage, bunkering, and utilization of green fuels, because not all hydrogen is used directly as a fuel or combustion or being transported to Germany. Of course, there's a huge interest in upgrading these to green fuels. That's a complex area. We also have projects across electrolyzers, hydrogen purity, how impurities in the gas will affect materials. And these impurities can, of course, be added on purpose, but also if you reuse existing infrastructure, you might have impurities picked up by the hydrogen gas. And complementary, we also work a lot with CCS, carbon capture and storage, and have state-of-the-art test facilities within this area, if that has any interest. But we also always on the outlook for new project partners. So if you have any ideas or would like to participate, then please get in touch for future projects with us. An example of one project we conducted with 14 partners was documentation demands for hydrogen infrastructure, because there was a stage where a lot of, especially in Danish industry, were trying to navigate what is out there now, what is available of guidelines, standards, and what is best practice. And that was ended up being a report published last year. Right now, we're continuing this work with an actual test program. So that's a new phase 2 project ongoing, in order to supplement the literature-based approach with reliable test data, the right test data, because when you test a material in hydrogen, it's quite easy to show that hydrogen can cause cracks and damage. But where is the limit, and how can we apply this in the real world? That's our main interest, really. Another example is safe and fast implementation of Power2X, which is a project where a report was just released. If you're interested, the QR code leads you to the download site, but you will get the slides afterwards, so no stress. Then we're also participating in World Hydrogen Week in a few weeks, so we hope to see some of you there. We will have a stand at the expo and have a presentation on October 3rd. So we might meet and discuss topics with some of you there. We hope to see you anyway. And then again, how do we close these gaps? Well, we've made this mini guide. It does not cover everything, but we try to cover aspects of what you need to consider: the risk screening, the material screening, the definition in terms of hydrogen readiness, because we have seen a lot of insecurity because you can buy hydrogen ready components or other purchases, and there's really no definition of what does that cover. It does not refer to specific testing, specific standards. So right now it is a jungle out there, and we would like to help you navigate that jungle. So keep an eye out for news from us, and you're more than welcome to reach out, download the mini guide, contact us. So I guess that was it from us for now, and you can see all our emails. You're more than welcome to write any questions that you might have, and if there's anything in the chat, we will get back to you and reply to your questions and comments. So thank you everyone for listening in. We did not spend the whole hour, but that was not the plan anyway. So let's keep in touch, and thank you for joining us today.